Welcome to Digital System Design course, Module 5, Session 4. The contents of Session 4 are design of iterative circuit. First, we'll understand the meaning of iterative circuit. As an example of iterative circuit, we'll see how to design a comparator which compares two n-bit binary numbers. First, we'll see the meaning of iterative circuit. An iterative circuit consists of a number of identical cells interconnected in a regular manner. As it says here, number of identical cells. Now consider the example of binary addition. Now here, in order to perform the binary addition, the same operation is performed on each pair of input bits here, right? Now, the diagram which is shown, the first diagram is shown, is that of a unilateral iterative circuit. We call this as a unilateral because the signals move from left to the right here. Now, if you see, each cell is a combinational circuit which possibly takes one or more primary inputs and possibly generates one or more primary outputs, and it can take one or more possible secondary inputs and possibly can generate one or more secondary outputs here. As an example of iterative circuit is that of a parallel adder, which is a 4-bit parallel adder, and since it is a 4-bit, it consists of 4 full adders here. Now we know the what is iterative circuit. Now we'll see why iterative circuit is more suitable for comparing two n-bit binary numbers. The first question comes to our mind is why iterative circuit here. As we saw in previous, I think module 2, we've designed 1-bit comparator, 2-bit comparator, and 3-bit comparator. As the number of bits for comparison increases, the complexity of designing that will also increases here. So that as when n is 4 or 5 or beyond that, the direct design approach is not practical. And the better solution for this could be an iterative approach. Now we'll see how to design this n-bit comparator using iterative approach. Now, as I said here, we'll compare two n-bit binary numbers, and these two binary numbers are designated as x and y, and each are of length n, x1 to xn, yn to yn. The diagram shown here is that of an iterative circuit for comparing two n-bit binary numbers. And here the comparison proceeds from left to the right. The MSB bit is given to the leftmost cell and the LSB bit is given to the rightmost cell here. And all these inputs x and y, which is of length n, are applied in parallel to all of these cells here. Now, as I said here, the comparison is performed from left to the right here. First, the MSB bits x1 and y1 are compared, and the result of that is given to the next cell. Result of that is given to the next cell, and this cell has received the input x2 and y2, and the result of this comparison is given to the rightmost cell. Similarly, the MSB bits are also compared, and the result of that is given to the output circuit. Now this output circuit will generate 3 outputs, and these 3 outputs are designated as Z1, Z2, and Z3. Now this Z1 bit will be set to 1 if the binary x is less than y, and the bit Z2 is equal to 1 when x is equal to y, and Z3 bit will be set to 1 when x is greater than y here. Right? Now, everyone understood how the comparison is performed. As I said here, the comparison is performed from left to the right. The first, the MSB bit is compared. After that, the next lower bits are compared, and lastly the least significant bit is compared, and the output is given to the output circuit, and depending on the comparison it will generate the output Z1, Z2 and Z3, saying whether X is less than Y, X is equal to Y, and X is greater than Y here. Now since we know how the comparison is performed, now we'll come with a state table for this comparison. Now here, as I said here, the input conditions what we have is X is equal to Y, X is greater than Y, and X is less than Y. And for these three input conditions, will designate the states as S0, S1 and S2. S0 is for X is equal to Y, S1 is X greater than Y, S2 is for X less than Y here. Now we'll come with the next state for this one. Now how? Now the inputs what we have is Xi and Yi here. Now here we'll go back to the previous slide. I'll explain here. Now here, as I said here, this is a MSB bit. We'll take this one as something like 1, 1, maybe 1 here. We have 0 here, or 0 here. And this is also what we have, 1, 1, 1. Maybe now it is 1 here and it is 0. As I said here, the first MSB bit is compared. These two bits are compared. And now here what will happen, since X1 is compared with Y1. Now here, as I said, the result of this comparison is given to the next cell, and it says that X is equal to Y. Next, again, now X2 is compared with Y2. Again, X2 is 1, Y2 is also 1, so that X is equal to Y. Next, again, what we have, this is compared here, right? X3 is compared with Y3. Again, X is equal to Y. Now what we have, X4 is 0 and Y4 is 1. We know that since Y4 is 1 and X4 is 0, so that what will happen here? Now X is less than Y here. And irrespective of the lower bits, maybe take an example that this XY is 0, X6 is 1, and the X7 is also 1. And this could be still be 0. X5, X6, and X7 could be 0 here. Still, we know that since this Y4 bit is 1 and the X4 bit is 0, we know that X is less than Y here, right? So that irrespective of the comparison of the lower bits here, as we know that this is the most significant bit now. Here, we know that till here, X1, X2, X3, Y1, Y2, and Y3 all are equal. But here, when it comes to this bit, X4 and Y4, Y4 is 1 and X4 is 0. So that we know that X is less than Y. Irrespective of the lower bit, this condition will still remain the same here. Right? Now, one more. Now, we can have something like this one. 1, 1 here. 1, 1 and 0 here. Now again we have 0 here. This is 1 and 1. We have 1 and 1. Now the first bits are compared. This one and this is compared. X is equal to Y. The next X2 is compared with Y2. X is equal to Y here. Again X3 and Y3 are compared. Now X3 is 1. Y3 is 0 here. So that what will happen now? Since X3 is compared with Y3, we know that X3 is greater than Y3 here, right? Now, irrespective of the comparison of the previous bits, since as compared to all these bits, this is an MSB bit, right? This is the most significant bit compared to these bits. Similarly, this bit is the significant bit as compared to this bits, so that since x3 is greater than y3, irrespective of the comparison of the lower bits, this x will always be greater than y here, right? Have you understood this one? Now with this understanding, now we'll fill the state table for values of x and y. Now, now we'll see. Now we have here SI is the present state is yes not, and the inputs what we have, which is xi and yi, is 0 0. Now what is the next state when the present state is yes not? Now when I say yes not, it means that x is equal to y. It means that you compared all the bits till now, and we know that x is equal to y. Now again the input what we have is xi is 0, yi is also 0. Since both are 0, the next state is also equal to yes not here. The next state is also equal to yes not. Now when the input is 0 1, it means that the x is 0, y is 1. Now what is happening here? Now y is 1, x is 0 here. Till here we know that the x was equal to y. Now y is 1, x is 0. So that we know that x, now we know that x is less than y. Since x is less than y means which is the state we have it? X is less than y, it is yes2 state. So that the next state will be yes2 here. Right? Similarly, if the input x is 1 and y is 1, since the present state is yes not, which is for x is equal to y, the next state will also be equal to yes not because it is for x is equal to y. Now if the input is 1 0, if the input is 1 0 here, no, x is 1, this is nothing but x here, right? And this is nothing but for y, right? Now x is 1, y is 0. So then which is the next state? We know that now x is greater than y. So that for x is greater than y, which is the state we have it? Yes, 0. So that if the present state is yes not and the input x is 1 and y is 0, the next state will be yes 1 here. Right? And since x is equal to y, as I said from the diagram, we know that z2 will be set to 1 when x is equal to y, so that this will be equal to 1. Similarly, now if the present state is yes1, when I say present state is yes1, it means that x is greater than y. It means that the most significant bit comparison says that x is greater than y here. Now if the lower bits, which is xi and yi, is 0 0, right? Irrespective of the comparison of this one, we know that since the present state is yes1, which stands for x is greater than y, it means that the most significant bits is already compared, and it says that the most significant bit x is greater than y here, so that the next state will also be equal to yes1 only, because the comparison depends on the most significant bits here. Now if the lower bits are still 0 and 1, x is 0, y is 1, still the next state is equal to yes1, because the comparison still depends on the most significant bits. If the lower bit is 1 1 also, the next state still is equal to yes1, because it still depends on the comparison result of the most significant bits here. And if it x is 1 and y is 0, the next state is still equal to yes1. Since x is greater than 1, which bit will be set here? As I said, it is the bit z3. Next, now the present state is yes2. What is this present state yes2? What do you understand by this one? It means that x is less than y. What do you understand by X is less than Y here? It may take an example of this one now. We have, as already explained in the previous slide, we'll make this as 0 here. This is 1, this is 1, and this is 1. This is for X, and this is for Y. Right. Now, next what we have it as, we have it here 0, 0 and 0. Next what we have 0, 1, 0, 1. Next what we have is 1, 1, 1 and 1, 1 and 0. Now first these two bits are compared, X is equal to Y. Now this is equal, we already studied for equality when the present state is this one. Now here, for till now it is this one, right? Now here what we have it now here, this one, right? We have 0 here and this is 1. X is 0, Y is 1, right? Now what we have, what is happening for this one now? As I said here, we saw the scenario for this one here, right? 0 and 1. It will go to the state S2. S2 state is nothing but for X is less than Y. So that now what is happening? X is 0, Y is 1. So that what is the result then? X is less than Y here. Now since these two bits are more significant bit as compared to these bits here, this will become the least significant bits compared to this one. So that irrespective of this comparison, we have 0, 0 here, 0, 0, 0, 1, 1, 1 and 1, 0. As we know, since the most significant bit here is 0 and 1, and since X is 0 and Y is 1, the result will always be X is less than Y. So that the previous state, irrespective of the lower bits, whether it is 0, 0, 0, 1, 1, 1 or 1, 0, the next state is always equal to S2, S2 here, S2 and S2 if the present state is already S2. And what is the comparison result for this one? Now Z1 will be set to 1 for this. Okay. Now we'll come with now we prepared this state table. Now for this table, we'll come with the corresponding transition table. Now, in order to come with a transition table, since how many states do we have it here? We have 3 states, S0, S1 and S3. Since there are 3 states, there are 2 intercell signals, and those intercell signals are designated as AI, BI. Right? And we know that here, this is nothing but we replace that S0, S1 and S3 with 0, 0, 0, 1 and 1, 0. Now, this is nothing but what? Yes, 0. This is S1 and this is S2 here. AI, BI is 0, 0. AI, BI is 0, 1. AI, BI is 1, 0 here. Right? Now, looking at the state table, now what we do? We replace this S0, S1 and S2 states with 0, 0, 0, 1 and 1, 0 respectively. Now, for the input 0, 0, 0, 1, 1, 1 and 1, 0, we've written the next state in the state table. Now we replace the states with these values now. As I said here, now here S0 is replaced with 0, 0 and S2 is replaced with 1, 0 and S0 is replaced with 0, 0 and S1 is replaced with 0, 1. And we know that when it is in this state, it is in S1 state, irrespective of the lower bits value 0, 0, 0, 1, 1, 1 and 1, 0, it will always be in S1 state. S1 state is nothing but 0, 1, 0, 1, 0, 1, 0, 1. We already know about this output bits here. And similarly, S2 is replaced with 1, 0, 1, 0, 1, 0 and 1, 0. Now, once we have the state transition table for this one, now we'll come with a The next state equations. How do you come with the next state equations for this one? With the help of a K-map. Now, how do you fill for this one now? The values here. Now, if you see this one, now we have here, we have this is for xi, yi, this is ai, bi. And what the values we have 0, 0, 0, 1 and 1, 0. We don't have 1, 1. Since for 1, 1 condition, we put it as x, which is nothing but the don't care terms in the K-map. Now, since we're coming with this, the next state equation for ai plus 1 here, we substitute these values. In the K-map. Now what we have when ai, bi is 0, 0, next what we have 0, 0, 0, 1, 1, 1 and 1, 0. What we have is the value 0, 1, 0 and 0. This comes in the first row, and the second row what we have 0, 0, 0 and 0. And you can see here we don't have 1, 1, and for 1, 1 we put don't care condition in the K-map. And next for 1, 0 what we have 1, 1, 1 and 1. Right? Now we'll come with the next state equation using the K-map for ai plus 1. So the substitute the values here, what we have 0, 1, 0, 0, 0, 0, 0. As I said, for 1, 1, we put xx, which is the don't care terms. And for 1, 0, it is 1, 1 and 1. Now, how do you do the grouping? Go for maximum grouping for this one. And what is the expression for this one? It is 1, 1 here, and it is something but for ai. Or now here, how do you group it here? These two cells are adjacent, so that what is the common term we have it here? Here for this one, it is 0 and 1. 0 and 1 is what? 0 is xi bar yi, and which is this common here? We have 0, 0 and 1, 0. 0 is for bi, so that we write it as bi bar. So that what is the next state equation for this one? ai plus 1 is equal to ai plus xi bar yi bi bar here. Similarly, looking at the transition table, now write the state equation, the next state equation for bi plus 1, substitute the values in the K-map, simplify this one, and what is the expression you get here? bi plus 1 is equal to bi plus xi yi1 ai1. Now, yeah, this is the implementation using NAND gates for one cell. Now, similarly, we did for the next state equations for ai plus 1 and bi plus 1. Similarly, we do it for the output circuit. Now, how do you find the next state equations for the outputs zi, z2 and z3 using the K-map? Looking at the transition table, substitute the values in the K-map, simplify this one, so that what is the expression we have it here? What we have? We get the expression as z1 is equal to an plus 1. Now this is z2 is equal to what? An plus 1 bar bn plus 1 bar. Similarly, for z3 you get it as bn plus 1. And the output circuit for this comparator is shown in the figure here. As you can see, z1 is nothing but an plus 1, and here, and this is what we have it, z2, and we have bn plus 1 here. Now we have seen how to design a combinational comparator. A sequential comparator is similar to the combinational comparator what we studied. Here, if you see here, as I said here, in combinational, the comparator what we studied, all the inputs, the xi and yi are given, are received in parallel. But when it comes to sequential comparator, these inputs xi and yi serially, are received serial here, and the state equations, the state table still remains the same as what we studied for combinational comparator. And also if you see the typical cell forms the combinational part of the sequential circuit here. And assignment, design the sequential circuit for n bit binary comparator. Thank you.